Okay, so here's where we're at. Now you all have the skills to do labs, okay? Now we're going to take all of that and begin to put it into applications, all right? So if you want to plan ahead, your first big test is going to be a week from tomorrow. Now, you can get the test done during planning, during this time. You have to work fast, but you can easily get the test done. So if you want to have a more relaxed time, just realize you might want to plan on staying after school on Friday. Okay? You can get the test done, but you got to work fast to get it done. Okay? And I'm not saying super fast. You just got to clip right along. So I'm just telling you, if you want more time, make arrangements next Friday where you can stay after school to finish the test. I'm just giving you that as an option. Okay? I'm not going to say, hey, the bell was rang, soon you have to have the test done. So if you like more of a relaxed thing where you don't have to feel rushed, that's an option. Okay? Just saying. Now, I'm not going to stay here till 7 o'clock and order pizza. Okay? There is a limit to that, all right? But I'm just saying, so if you want to plan ahead, if you ride the bus, you want to make arrangements for a different way to get home, I'm just telling you now so you can kind of begin to think that through. Okay? If you don't have to, I'm just giving that out as an option. Your brother was famous for staying after tests. Like he would literally stay till 5 o'clock. We would place a betting pool on how long it would take for him to finish his test. Ask him about that. Okay. All right. Let's talk about the lab. So what you're going to do is you're going to take a cart like this, and there's going to be like 5 or 6 of you in a lab group. This takes a lot of time. So what you're going to do, the short version is you're going to push a cart like this with the plunger, and you're going to push it. It's going to roll into the wall. It's going to hit the wall, and then it's going to bounce back. Okay? So this is going to be important. Is the cart going to change direction? So what does it have to do? Stop. And speed back up. Okay? So something has to make it slow down, stop, and speed back up. And that's the role of the plunger. Okay? So when this thing is rolling along and the plunger hits, and we'll spend a lot more time talking about energy. Basically what happens is that you're transferring kinetic energy, which comes from the Greek word kinesis, which means motion. You're transferring kinetic energy into potential energy in the spring. Now, Mother Nature doesn't like potential energy. Something was said on Snapchat, Twitter, they wore the same dress to prom. I don't know, okay? They don't like each other. Never have, never will. Mother Nature and kinetic energy, they're besties. So when Mother Nature senses that that potential energy has been stored, she changes it back into kinetic energy. Okay, so you go from kinetic, potential, boom, back to kinetic. So here's what I want you to think here. We're going to kind of piecemeal this together. So I'm going to roll the cart. Let's say this direction is positive. So I'm going to roll the cart in this direction. Now, for the sake of this lab, we're going to assume that the cart is already moving. We're going to push it from the rest, but that's not what we're going to consider. Okay? We're going to consider that the cart is already moving when we start the analysis. That means your velocity time graph is not going to start at 0, 0. The cart is already moving. Okay, so imagine this. I'm going to give this cart a push, and then I'm going to stop it. Okay? So what would the position time graph look like, assuming that I am going to start the position time graph at 0, 0? So what would the position time graph look like for me pushing it and then stopping it? Here's your position time graph. It's going to start at 0. What's it going to do? Go up, and then I'm going to stop it. Once I stop it, what's it going to do? Something like that? Okay? At my age, don't say flat line. At my age, that's just a little sensitive. Like, oh, it flat lines. No, don't say that. I'm about to turn 60. Bad. Okay? We can say it levels off. We can say it plateaus. Just don't say it flat lines. Now, what would the velocity time graph look like? It's already moving, and we're finding this direction as being positive. It's going to start here. It's going to slow down a little bit as we go, and then I'm going to stop it very quickly. I heard something like this. Seem reasonable. It's going to slow down a little bit as it rolls. So I'm going to have some negative acceleration with positive velocity. That's going to make it slow down. Then, bam, I'm going to stop it. Once I stop it, it's going to come to a rest very quickly, right? So then, I'm still going to have negative acceleration, but now I'm going to have a big negative acceleration with positive velocity, and then it's going to slow down very quickly. So I'm going to slow down, I'm going to slow down, I'm going to come to a stop. Okay? If you were to find that area, what would that represent? How far it rolled. Okay? Cool. So that's if I just roll it and stop it. Okay? If I just roll it and stop it, that's what it's going to do. Now I'm going to change it up. So now I'm going to roll it. I'm going to have it hit my hand, and then I'm going to have it bounce back. Okay? So I'm going to go yoink, hit my hand, rolls back. Now what's my position time graph going to look like? Sebastian? That?
Yeah.
Beautiful. Why?
Because it goes back to the way.
Yeah, it changes direction. So this is going to be important. This cart is going to change direction, which means it has to slow down, stop, and speed back up. Okay? So, since it has to slow down, stop, and speed back up, that's what's happening here. At the very top of that line, I can draw a tangent line which has a slope of 0, which means my velocity goes to 0. I have positive velocity, then I have negative velocity. All the criteria have been met to show a change in direction. I slow down, stop, speed back up, my velocity changes sign. I have a tangent line of 0. Math nerds, I have a relative maximum. Okay? Cool with that. Now, what's the velocity time graph going to look like? It's going to start with some positive velocity.
Slightly down.
Slightly down. Shoot up, shoot down.
Shoot down.
Okay? So, here's the question. When this thing hits at this point, that's what's making it slow down, because this plunger is going to hit the wall. And I'm going to convert kinetic energy into potential energy. So at this point right there, that's when the plunger hits the wall. Now, very rapidly, it's going to slow down. That's when I'm storing that energy. So now this is where this spring is being compressed. I'm taking that kinetic energy and I'm storing it as energy in the spring. But Mother Nature doesn't like it. So what's Mother Nature going to do?
Speed back up.
Push back, go in the opposite direction. So when that spring expands, what's the graph going to do? Is it going to spike back up, or is it going to keep going down?
Going down.
Mr. Jones, what'd you say?
Down.
Why?
Because it just goes back the other direction.
Yeah, because it changes direction. I have to cross through 0. So then, it's going to come down here like this. So this is when the spring is expanding. And then as it rolls back, it's going to do something like this, because it's going to slow down. So I'm slowing down as it rolls towards the wall. It's going to hit the wall at this point. Boom! Very rapidly, it's going to go to 0, stop, speed back up. So the spring is like horizontal gravity. But instead of gravity acting for a long time, it happens very quickly. Thank God gravity doesn't act that quick. Because if gravity acted as fast as the spring did, I'd throw it up and go bam, come right back out. Okay? Playing basketball, any sport would be very, very difficult if gravity acted like that. Okay? Hit the ball, boom, comes right back in. So, this is when it's going to leave the wall. And now, this is just when it's rolling back along. From here to here, am I speeding up or slowing down? Speeding up, because I have negative acceleration with negative velocity. So I'm slowing down, bam, I speed up. But then what am I doing here?
Oh, no.
Slowing back down again. So what's the only time when that thing rolls and bounces back, what's the only time it speeds up?
Right after it bounces.
You got to be more specific than right after the wall.
Right after it.
Nope.
When the spring expands.
When the spring expands and it's pushing against the wall. Okay? When you answer these questions, in terms of this analysis, you have to be very specific. You just can't say, oh, when it's at the wall. There's a whole bunch of things that are happening at the wall. You have to be very, very specific about that. Now, this is why this is going to take like 5 or 6 people per group. What you're going to do, and let me hand out the lab so you have it.
The graph is experiencing tachycardia, blood pressure of 140/90.
Yeah, I was trying to grab this big.
Gotcha. That's what I was doing. Okay, so here's what you're going to do. In terms of getting the data, you're going to find space on the wall, have 5 or 6 people per group. There's about 20 of you here today, so like 4 groups of 5. Okay? So here's the wall. What you're going to do is you're going to measure back 1.5 meters, and you're going to put down a piece of tape. Then you're going to measure another 1.5 meters, put down another piece of tape. Okay? So you're going to end up a total of 3 meters away from the wall. But we're going to make this point the reference point. Okay? That's going to be 0. So where you start the cart is going to be 0. Then it's going to go to a point of 1.5, and then it's going to go to 3 meters. So you can go from a position of 0 to 1.5, 1.5 to 3, then you're going to go from 3 back to 1.5, 1.5 back to 0. So you're going to have 4 different increments. Okay? And you're going to have somebody time each increment. Okay? So like Katie might time from 0 to 1.5. Mr. Jones might time from 1.5 to 3. Teague might time from 3 to 1.5. And somebody else is going to time from 1.5 back to 0. So Elizabeth is going to time that, okay? And then we're going to look at the entire time, okay? So this is why you need like a minimum of 5 people. So somebody timing each interval, and then somebody keeping track of the entire time of the trip. When you're doing this, make sure everybody goes off the front edge of the cart, okay? And you want this cart moving when it crosses the 0 mark. Don't put it at 0 and push it. You want it moving when it crosses this point. That's why the velocity time graph doesn't start at 0. So, what you're going to do is that we're going to assume over this relatively short distance that we're going to calculate velocity using displacement over time. Now, technically, displacement is position final minus position initial over time. So, on the way in, you're going to start at 0, and then you're going to end up at 1.5. Okay? So on the way in, your initial position is 0, your final position is 1.5. So if you're timing that, you're going to start the stopwatch when it crosses the 0 mark. You're going to stop it when it crosses 1.5. So your displacement calculation is going to be 1.5 meters minus 0 over however long that took. Okay, let's say it's a second, whatever that time is. Okay, so then your velocity is going to be over that interval 1.5 meters per second. But keep in mind you're slowing down a little bit. So you're probably going a little bit faster than that at the beginning, a little bit slower than that at the end, but on average, you're going like 1.5 meters per second. So then you're going to time it from 1.5 to 3. Again, you need to calculate the displacement. Oh, that displacement calculation, and I tell you, in big bold letters, be sure to show any calculations. You need to show me 8 calculations. 4 calculations of displacement, 4 calculations of velocity. Okay? So on that second displacement calculation, all you have to do is take 3 meters minus 1.5. That's your displacement on the second interval. Now, it gets weird on the way back, because on the way back, you're starting at 3, and you're ending up at 1.5. And then you're starting at 1.5, and you're going to 0. Okay? So on the way back, you're going to take 1.5 minus 3, and then you're going to take 0 minus 1.5. So what's going to happen to the sign of your displacement on the way back? It's going to turn negative. So guess what? When you divide by time, now you're going to get negative velocities. Okay? So that's how you're going to go from positive velocities into negative velocities. So let's just say that that first interval took 1 second and that second interval took 1.20 seconds. I'm just making the time. So here you're going to write down those individual times. Then you're going to add those together to get that entire trip. What you want to do is compare the entire, when someone's keeping track of the entire time, start to finish. When you add together the individual times, it should be within 1/10 of 2 of the entire time. That's why you want to keep track of the entire time. So you can compare it, make sure somebody didn't screw up one of the intervals. Okay? Your lapse time is going to be a running total. So I'm going to have 1 second, and then I'm going to have 1.2. So at the end of that second interval, I'm going to add those together, and I'm going to get 2.20 seconds. That is the most critical time that you need when you draw your graphs. That's when your velocity goes to 0. So this is why I say this is the most critical thing. So at 2.2, that's when my position time graph is going to break over center. On my velocity time graph, that's at 2.2 seconds. That's when that's going to go through 0. Okay? So the end of that second interval is the most critical time that you have. Okay, I'm done. So get your marks on the tape. There's tape. The carts are back there. The stopwatches are back there. Put down a mark at 1.5. Put a mark, another mark at 3. Get your times. Don't push this very fast, or this cart gets all wonky. Okay? You want to make it where it just barely makes it back across the wall. Ready? Break, go. So keep off on the camera. So 4 groups. Figure it out.